So I work as an economist at Amazon. My area of expertise is in causal inference. And what I'll be talking about today is how machine learning methods can be applied to causal inference problems. I'm not look if that's interesting, just to keep up the slide. I think most of the audience probably is familiar with machine learning in general. So as a standard problem, what we usually focus on in ML is prediction. And so broadly speaking, you can think of that as being you have some X, some features that you think are predictive of a Y, and you want to make your best guess as to what that Y is given this X. And generally, there are good ways to test what models are working and what models are not working. So you can kind of test the accuracy of your model or your method against some source of ground truth. So very simple kind of situation, you're trying to predict the price of some stuff. You have historical actual prices, so you can always compare to see how well you are performing. And causal inference is a more challenging problem. It's asking a different question. It's looking at how would the y value change if you were to change the x value. And usually in such situations, the x is a variable that you have some control or some influence over. And so the idea is that you want to be able to change x to optimize y in some way. And you want to understand what is the sensitivity level. So if I change my x by 10%, what is the expected impact on y? And generally, if x is causing y, then x will be a feature that will help you predict y, but it's not true the other way around, and I'll show you some examples of what that looks like. And in causal inference, it can be very difficult to validate a solution. There is generally no source of ground truth. You cannot, unless you actually try to change your x and see what happens, you can't know beforehand whether your method is properly estimating that effect or not. So these approaches that are used to solve this kind of problem are generally very heavy on assumptions, and these assumptions are not usually going to be testable. And so that makes it a pretty challenging problem space to work with. So if x predicts y, it does not mean that x has caused y. And it does not give you information on how y would behave if you were to change x. So to put this back in the ML space, so let's say you have data on a particular set of x values and a particular set of y values. If I was to kind of try to train a model in a particular region of those covariates, and now I will move to an entirely different section of the feature space, there's no reason to think the model will continue to perform as well as it does in a particular area. So ML models can sometimes fit to local effects. And this is even worse in causal inference. So just because you have some information on the predictive relationship between x and y, it will not tell you how y changes as x changes. And it will not in particular help you to choose the best x. And in these kind of problems, it's generally not of sufficient interest to understand that x predicts y. You might want to understand why the x is affecting the y. And this becomes more important when you're thinking about choosing the best x. And so it's a problem that is more challenging because you need more information than purely a prediction problem would require you to have. But it is more useful. So in the technology sector, usually we think in terms of changes to a particular product or changes to a particular feature or an app. And when you're making those changes, you need to be able to justify why you think it's going to have an effect and why the effect that you're estimating makes sense. So what is kind of the channels through which it works and what is the business logic for why it is making a difference. Next one. Okay, so I mentioned that just because something predicts something else, it doesn't mean that either one is causing the other. So this is a contrived example. So what is plotting in the chart here is arcade revenue versus CS doctorates in the US between 2000 and 2009. So it's like a pretty famous example, so I think some of you may have seen it before. But the idea is generally like just eyeballing it, you can tell that either one of these variables would predict the other with very, very high accuracy. But this doesn't actually give you anything useful from a strategy perspective. So should you, for example, start building more arcades to encourage more computer science PhDs, or should you be subsidizing PhD programs because you want to increase arcade revenue? Like neither of those things makes any sense. And building arcades is not going to drive the next computer revolution. So the idea I'm trying to get across here is that looking purely at correlation and prediction is not prescriptive and will not give you information on what you should be doing. So you can kind of rationalize why you might be seeing this pattern. So like there may be some third variable that predicts both of these or causes both of these. So for example, like post.com, maybe there's some sudden second surge in kind of interest in information technology. That leads more people to study computer science, and it may also lead to more innovations in arcades, and therefore more people go to arcades. So there may be this third variable that is kind of causing both of these, and so if you did not know what that third variable was, or you weren't able to observe it, you can't really do too much just by looking at this pattern. Okay, one more example. So this one is plotting divorce rates in the state of Maine against margarine consumption. I think this is average household margarine consumption in the same state. And the point I'm trying to make here is that the underlying latent feature that causes both of these is sometimes very difficult to isolate. So here, like, I have no idea, I don't know if anyone else can come up with a good explanation as to why these things are so strongly correlated. And so this is another contrived example, but this happens quite a bit. There's many examples of patterns that you'll find in your data which have no clear explanation. And so this is again a question of distinction, because if you were only interested in predicting margarine consumption and you had data on divorce rate, like, you don't need anything else. Like this within if you assume that this is kind of the structure of the data, this is all you need. But if you wanted to understand what causes this and what you can influence to try to change these values, that becomes a different problem, which is what we're going to try to focus on here today. So high level, when should you think of your problem as being something where causal inference is relevant? So I have a few examples up here. These are kind of coming from the tech world. So let's look at the first two. So the first one is, what product should you be recommending to a user? And the second one is, if a customer buys a phone, how likely would they be to buy a phone case? So both of these fit pretty neatly into a question of prediction. You can kind of look at historical behavior of a particular user or customer, and that can allow you to predict their propensity to, for example, buy a new phone case conditional on them having bought a phone in the past. And it might also inform what kinds of products they've been visiting, what pages they've been visiting, and correspondingly, which one should you be recommending going forward. The next three problems are not so easily solved using a purely predictive approach. So the first one is a famous one. This is something that Microsoft and Bing have been looking at, which is basically, should a blue color theme homepage drive more purchases? So on the surface of it, it seems like a pretty naive thing. Like do users really care about the color of the homepage? And it turns out they do. This is one of the most influential experiments that Microsoft has ever run. It generated a huge amount of money for them just by changing the color of some of their pages. And this was solved using causal inference approaches. In this case, they kind of did an A/B test, and that's what informed it. But this is a problem within causal inference. The last two are around pricing and promotions. So should you offer discounts on subscriptions to your product? And are Black Friday sales promotions worth it? So this is again challenging. Like, if you, let's say you have never run a promotion before, you've never run a Black Friday sales promotion before, and you want to decide, should you be doing it? So now you have no information on this at all. How would you think about solving the problems? The idea is, like, the promotion can be thought of as a kind of treatment being applied to your customers, so they see either additional information or they see lower prices. And what would that induce them to do? So what kind of behavior are you causing by doing that? And that's this last kind of problem space around promotions is what I'll focus the rest of my example on. Next slide. Okay, so in the spirit of Black Friday and sales promotions, so let's think of a simple case. Problem structure is like this. So some customers are exposed to a marketing campaign. To make things interesting, let's not call this a website campaign. Let's think of it as a combination of TV, maybe something on, like, the ads you see on Hulu, something like that. So what I'm getting at is, it may not be very easy for you to control who's actually seeing your marketing campaign. And so customer A is not exposed to the campaign, and that customer has a particular revenue, call it revenue A. And customer B does see the marketing campaign, and they have revenue B. And the question that you're trying to answer is the marketing campaign worth it? Like, should you have run it? Should you have invested in it? Next slide, please. Okay, so why is it an important problem? It's pretty self-evident. So marketing campaigns are costly, promotional offers are costly, and so you need to think about, is the investment worth it? Another question is, should we continue doing this going forward? Let's say we've done it one time and we kind of are trying to plan for, should we be doing this in the future? And let's say that, like as is realistic, usually you want to make these decisions very quickly. So let's say you had a Black Friday promotion last week, and now this is the week when everyone is meeting and trying to decide, should we ever be doing this again? And the final question you might want to answer is, let's say that the campaign was on average somewhat effective, but let's say there was a particular segment within my customer base for whom the promotions were very, very effective. So can we do a better job of targeting these kinds of things in the future? Okay, so coming back to the problem setting, so what we're observing here is, just to reiterate very quickly, customer A in row 1, they don't see the campaign and they have a particular subsequent spend or revenue. And customer B does get exposed to this marketing campaign and they have a different revenue. So this is what we observe, but it may not be the best thing that for us to want to observe. Next slide, please. So what we would really want to understand is, for a customer who is exposed to a marketing campaign, what would they have done had it not happened, had they not been exposed to my marketing campaign? And very intuitively, what this is telling you is, if you could see for every customer what they did with and without your marketing campaign, for any given customer, the difference in the values between those two states of the world, that is going to be the effect of your marketing campaign on that particular customer's revenue spend in the future. And so this is really what you want to observe. Next slide. And the problem is that you don't observe. So generally, if a customer is seeing a marketing campaign, they could not possibly simultaneously have not seen the marketing campaign. And this is true of most kind of problems in causal inference. If you have made an intervention or a treatment, as we also call them, generally a customer is either in one condition or the other, and you don't see both of them at the same time. And so this kind of leads me to the point where I make that causal inference can be thought of as a problem of missing data. If you were perfectly able to simulate customer B's behavior under all scenarios, you could construct a case with and without the campaign, and then the difference between those two constructed scenarios would give you the causal effect that you're interested in, the causal effect of the marketing campaign. So I mentioned it's a problem of missing data, and you don't necessarily have to think in these terms. Like, there are strategies that are very old. So RCTs, randomized controlled trials, A/B testing, those are very old and they've been around for a long time. And they kind of get around this problem by making assumptions on samples that are randomly chosen. And that can kind of allow you to sort of estimate that missing scenario that I talked about without actually having to model anything too heavily. But it's not always possible. A/B testing is costly, and it may not be possible to do depending on the specific problem. There may be ethical concerns. For example, if we're thinking about Black Friday promotions, it may not be ethical to show one person a price of $10, another person a price of $12 and $14 and so on. If you could do that, then you could run an A/B test, but it may not be possible. And then finally, it's a problem of scaling. Like, sometimes you don't have the bandwidth to get a large enough sample to actually run any experiments. And so then you want to think about purely observational data and how it can inform your decision. And so that's what I'm talking about today. Like, what we're focusing on here is observational causal models. And loosely speaking, what that means is we are not going to try to run any new analysis that requires us to intervene. So we're not going to try to run any experiments or control groups or anything like that. We're going to use the data that we already have collected to try to make an inference about the causal effect. And so this is a more general solution that is more broadly applicable. And the strategy that is generally used in this kind of setting is, we want to think about how to predict the missing data using the information we have to kind of guess at the feature of interest that we're missing. And so in the example that I'm talking about here, the feature of interest you're trying to guess at is what would the revenue of customer B have been if they had not seen the marketing campaign. And so now, if you can because we've kind of phrased this as a problem of prediction, this gets us back to sort of the realm of ML. And so this is where a lot of approaches can be very valuable. Okay, so the first one I want to talk about here is matching and clustering. So if you look at the panel at the bottom left, you can think of customers will tend to behave in particular ways. So for example, at Amazon, if you think of retail customers who are shopping, age and income are two major predictors of what kind of things people are buying, how often they buy, how often they shop. And so if you had enough historical data on your customers, you could think about grouping them into categories. So the idea is that based on my historical information that I've collected, customer A, B, C, D in the past, these guys have been behaving very similarly. They tend to buy the same things, they tend to spend the same amount. And if I can do this effectively, now when I run a marketing campaign and customer B is the only one who has been exposed to that campaign, you can think of the behavior of A, C, and D as in some way being representative of what customer B would have done had they not seen the marketing campaign. And so other customers in the same cluster as B can represent B's behavior without the campaign, and that can kind of allow you to make a guess as to what B's spend would have been had they not been exposed to the marketing campaign. And I've mentioned a few simple ways this can be done. So the first one focuses on matching, which is sort of trying to understand how you can create this cluster in a sort of I guess you have you have historical features. You're trying to look at what customers are most similar in terms of those features. So propensity score matching, or weighting of customers, or quotient exact matching. These are two strategies that are pretty popular in this kind of problem space. And then if we go more ML into sort of non-supervised clustering approaches, so you can think of k-means, hierarchical clustering. These are all similar in that they will tend to give you clusters that will help you solve the problem. Another way to think about identifying similar customers is, let's say we don't have any group of customers that is reasonably representative. So let's say we look at all our historical data and we find that A, C, and D are close to B, but they're not exactly the same as B. But now let's say we could construct a fake customer, a synthetic customer, who would be sort of represented by an average, a weighted average in some way of A, C, and D's behavior. And so you can construct a synthetic customer and you can train a model that will tell you what those weights should be. And once you have that, it'll give you a fake representation of customer B, and it would capture customer B's historical behavior that would be a good proxy for how they would have behaved without the campaign. And so the idea is it's a weighted average of your actual customers, and it can be done very flexibly. So the first time this approach was used was in political science research, where people were looking at tobacco taxes. And so that paper is a famous one. It's one of the first ones where synthetic control methods were used. And what they did there is they basically constructed a fake version of California, which is an average of other states. And the predicted behavior of that fake state was a proxy for how California would have looked if you had not had a tobacco tax imposed. So I talked a bit about clustering, matching, and kind of weighting approaches. Another way is to just kind of step out of that whole world and think instead about this as a very, very standard prediction problem. So you have a lot of features that would probably be helpful to you in predicting customer revenue. And you can think of deviations from your prediction as being attributable to new information that you did not have when you were training your model. So let's say I take customer A, B, C, D, I use all of the historical features, and I train a model, a regression model that predicts revenue. And if I was to run this model specifically for customer B to get predictions, I can think about those predictions against what customer B has done when being exposed to the marketing campaign. And so the marketing campaign was not included in the training data. It's some new information which affects B specifically. And so customer B's deviation from the prediction would be attributable partly to model error, but if you have a good model, that shouldn't be the main concern. But any further deviation could be attributed to the marketing campaign. And so this kind of general family of methods are meta-learners, and the idea is that it's very, very flexible. So there is no constraint on what kind of regression model you put in here, and depending on the kind of data you have, how much data you have, and what the structure of that data is, you can potentially go into deep learning and go into fully non-parametric methods. And so that gives you pretty powerful predictions of the missing counterfactual, the missing scenario of how customer B would have behaved that we do not observe. And the last one I want to talk about here is random forests. So random forests, intuitively, what any tree-based algorithm is doing is it's trying to sort of divide the sample space into sections. And the idea is once you get down to a leaf node, the conclusion of a particular tree path, customers or units or observations in that particular node will tend to be similar. And this is by construction because you've kind of been going through a process of filtering these customers. And so when you get to a leaf node, it's essentially solving a problem similar to clustering. Now those people who are at those nodes are going to be similar. And you can actually tweak the optimization function that we would normally use to produce groups that are not only similar, but would ex ante have had a higher expected causal effect. And so the reason we do this is because we want to isolate the customers who are most impacted by a treatment. So when I talk about sort of figuring out targeting, this is one of the ways in which you can kind of target. So the leaf nodes will end up producing groups that are very similar, and you can use also the whole random forest path to identify the features that are most important in isolating causal effects. And so the real value in these kind of approaches called causal trees or causal forests is that if you expect your customers or your users to behave very differently depending on certain characteristics, identifying those characteristics can get you to heterogeneous effects. So for example, I mentioned at Amazon, younger customers who have higher income will tend to behave a particular way. If I had a marketing campaign that affected that segment in particular, a strategy like this would allow me to isolate exactly how big the effect of the marketing campaign was for this particular group versus maybe customers who are older and who are not spending as much on the platform. So far, the previous slides are kind of thinking about how can we frame this as an ML problem and how can we solve it as an ML problem. So you don't, to use any of those previous approaches, you don't really need to know anything about the historical research or work that's been done in the causal inference space. But the fact is that some of these methods have been around for a very long time. So economics, social sciences more broadly. Causal inference is a pretty standard problem. A/B testing is done in in a randomized control trial format when you're thinking about new drug analysis. And so RCTs, differences, instrumental variables, these are all methods that are very old. And so besides replacing them, which is kind of what I've been talking about in the past, like I'd say these all have assumptions, they require specific settings and you may not be able to use them. So ML can help you replace them altogether, but ML can also work in conjunction with some of the older methods to provide better results. And so this is, it's like an area of active research, and so there's a lot of stuff going on here, so I won't go into too much depth, but the three kind of, I think, in my opinion, major ways in which machine learning can add value to standard methods in causal inference. So one of them is non-parametric fit. So a lot of these methods were developed in the 70s and 80s, so linear models were very much in vogue, and computationally speaking, that was the most efficient thing people could be doing. But in a lot of cases, there's no reason that a model has to be linear. You can think about non-parametric models that could do a good job, for example, fitting your data. And so machine learning methods here are pretty useful. So a lot of the most powerful predictive algorithms that we have can be substituted in for what used to be done in a linear model. I talked also briefly with the causal forest context about feature selection and interaction. So, for example, if we were doing an instrumental variables strategy, there are kind of certain things you have to assume around what variables you need to control for, what is the appropriate variable to include in the right-hand side of a regression. And so feature selection and interaction, that can be done as a pre-step, like isolating what features are actually going to be useful for you using machine learning methods before you actually go back to one of the standard methods. And another important one I want to talk to you about is something that comes up a lot in the tech context, which is measuring long-term effects. So let's say we were to run an A/B test. Let's say we were looking at a specific example of the change in the website color. So let's say I change the color tone of my website to blue, and I notice immediately that the people who see this blue page tend to engage more with it, and they tend to kind of have more activity on the page. But what does that actually mean over a 1-year horizon or a 2-year horizon? If I made that change permanent, like what kind of effects would I see in the very long term? And that's something that's usually not easily understandable just using the first three approaches, the more traditional approaches. Because these all use data that you've kind of gathered in the short term immediately after the intervention is complete. And it can be costly or time consuming to gather this over a longer period. And you may not have the time to wait. Sometimes you need to make the decision very quickly. And so figuring out a way to translate the output of a short-term model into a long-term effect, that's something that becomes very, very useful in a lot of different contexts. So the general family of models that solve this, they're called surrogate methods. And so, as I was mentioning, traditional methods will usually allow you only to measure the short-term effect. And what a surrogate model will do is quantify the relationship between short-term effects and long-term effects. So the idea is that you have been able to use some model, whether it's a traditional approach or a non-traditional ML approach, to estimate short-term outcomes. So that's kind of, if you look at the diagram at the bottom, like, so you have your marketing campaign, you've got the lifts on the specific surrogates that you've been tracking in the short term. And now what you're trying to get to is the thing on the far right, which is the long-term causal effects of the marketing campaign. So if you had a Black Friday sale for customers on one particular Friday in one particular year, what does that mean for purchasing behavior 6 months from now? And if it was the case that Black Friday shopping will kind of get people more engaged with your platform or much more engaged with your product, and now they keep on buying. If they keep on buying either the same product or new variations, even if you made massive losses on the investment on Black Friday, it might still be worth it. So you have to kind of think about how you would translate the short-term effect into the long-term effect. And this is where you can think of a model standing in between them. So a model that takes as its inputs all the customer information you have available, as well as the lifts that you see in the short term, and try to use that to predict long-term causal effects. And so if you are able to do this effectively, this kind of becomes a workhorse tool to sort of get you to any kind of decision paradigm. So if you had to think of any kind of intervention or campaign or treatment effect that you're interested in measuring, you would just run it through this long-term model to figure out, okay, if I see my revenue in the next 2 weeks increasing by $20, that might mean a $200 increase over a 6-month or a 1-year period. And that would change kind of the assessment of is an investment worth it. I think I'm almost out of time, but I wanted to touch on one final thing. So I started this talk by saying that one of the features of causal models is that it may not always be easy to validate. There is no reliable source of ground truth. So in the marketing campaign example that I gave, you don't have any data unless you run the campaign in the past. You have no data on how people have actually behaved, and therefore there's no way for you to tell whether what you've modeled makes any sense and whether it's wrong, whether it's right. So figuring out the reliability and robustness of model output in these kinds of problems can be pretty challenging. And there are some general strategies that you can use. So when causal models are making assumptions, you can think about testing the assumptions directly. So when you think about randomized control trial, one of the major assumptions you're making there is that the randomization is done correctly. And it might sound silly, but a lot of times randomization is not easy to get right. So you end up having a control group and a treatment group that are actually quite different, and so they're no longer comparable. So testing these assumptions is important. Falsification tests is kind of saying, let's say I was to run my model through a case where there was actually no treatment effect. So if I was to try to predict the effect of a customer who did not see the marketing campaign using my causal model, I should get a 0 causal effect. If I did get a causal effect, that suggests that something's wrong. I'll skip the next two, but like going to the bottom, experimental validation and synthetic data. So A/B testing is sometimes possible, but it's possible only at a small scale. But you can still run your model through that small scale experiment and try to see, do you match up with what the experiment was saying? So you can kind of compare multiple causal models in this way to kind of see, are they giving you consistent output? And the final one, synthetic data, is essentially if I was to construct kind of cases, synthetic examples where I know a causal effect has to occur because I've constructed it to be the case, the causal model should be able to recover. And if it's not being able to recover that synthetic effect that you have created that you know is definitely going to be, for example, 10%, if you get something like 30%, then your model is wrong and you should be wary of using it. Yeah, I think I will stop and about that. Yeah, thank you very much. And I don't know if I have time to go.